For most of human history, the universe appeared to us as a distant and largely unchanging backdrop, a vast stage upon which familiar physical laws played out in predictable ways. Yet each major advance in our ability to observe reality has quietly overturned that comfort, revealing that what once seemed stable is layered, dynamic, and often governed by mechanisms that resist intuition, where light behaves less like illumination and more like a historical record, where distance is inseparable from time, and where observation itself becomes a limiting factor rather than a neutral act, forcing us to confront an unsettling idea that our picture of the cosmos is not constrained by what exists, but by how far our instruments can reach before signals dissolve into noise, assumptions harden into models, and unanswered questions begin to accumulate faster than confirmed explanations, leaving us to wonder whether the universe we describe is a faithful reflection of what is out there, or merely the narrow slice that remains visible once expansion, scale, and the finite speed of information have already filtered most of reality beyond our grasp. And once that possibility is taken seriously, the act of observing the universe can no longer be treated as a passive window into objective truth, because modern astronomy is built on a chain of assumptions that quietly shape what we are even capable of noticing, beginning with the simple fact that we never see objects as they are now, but only as they were when their light began its journey toward us, meaning that every image, every spectrum, and every measurement is already a compromise between distance, time, and decay, filtered further by instruments designed with specific wavelengths, sensitivities, and theoretical expectations in mind, which forces science to operate within a narrow corridor where data must be interpreted through models that simplify complex systems into something mathematically manageable, even when those simplifications hide entire categories of behavior. And as observations push farther outward and further back in time, those models grow increasingly fragile because the conditions they were built to describe, local physics, familiar matter, stable structures, may no longer apply, leaving researchers to infer unseen processes from incomplete signals, to reconstruct histories from photons stretched, scattered, and distorted by expansion, gravity, and intervening matter, all while knowing that the universe does not present itself evenly or conveniently, but reveals only what survives long enough and travels far enough to be detected, which raises a deeper contextual problem that sits beneath every modern discovery, namely that our most confident conclusions often emerge not from direct observation, but from the absence of expected patterns, from anomalies that violate predictions, or from faint statistical excesses that suggest something is missing, something unaccounted for, something that refuses to appear despite its apparent influence. And this is why progress in cosmology is less about accumulating clearer pictures and more about negotiating the boundary between what can be measured and what must be inferred, a boundary that shifts with each new instrument, yet never disappears. Because even the most advanced telescopes do not simply extend human vision, they impose new constraints, prioritizing certain questions while rendering others invisible. And as a result, the universe we describe is shaped as much by technological reach as by physical reality, placing us in a position where greater clarity paradoxically reveals deeper uncertainty, and where expanding our observational horizon does not resolve ambiguity, but instead relocates it to a more distant, more abstract frontier, one where the limitations of method begin to rival the mysteries of the cosmos itself. And to understand how this boundary between measurement and inference first takes shape, it helps to begin not at the edge of the universe, but much closer to home, in regions where physics is well tested and structures appear familiar, because nearby cosmic environments act as calibration points that anchor our expectations about how matter behaves under gravity, radiation, and time, allowing astronomers to observe processes such as star formation, stellar evolution, and galactic dynamics with a level of detail that feels almost intuitive, where clouds of gas collapse under their own weight, temperatures rise, nuclear fusion ignites, and stars enter life cycles that can be modeled, predicted, and compared against observation. Yet even here, certainty is more fragile than it appears, because these processes unfold behind veils of dust, magnetic turbulence, and chaotic feedback loops that obscure direct measurement, forcing scientists to rely on indirect signals, spectral fingerprints, and statistical reconstruction to infer what cannot be seen outright, meaning that much of what we consider well understood is in fact an agreement between theory and incomplete evidence, rather than a direct visual account. And this becomes particularly clear when examining how light interacts with matter in these regions, since visible wavelengths are easily scattered or absorbed, hiding critical stages of development and giving a misleading impression of emptiness or simplicity. while infrared and radio observations revealed dense structures and energetic processes that were always present but previously inaccessible, quietly demonstrating that observational blind spots can masquerade as absence, and that our confidence often reflects the limits of detection rather than the limits of reality itself. A pattern that repeats across nearby galaxies, where rotational curves, stellar distributions, and emission spectra suggest coherent systems governed by gravity. Yet subtle discrepancies emerge when mass inferred from motion fails to align with mass that can be directly observed, prompting the introduction of corrective assumptions that preserve existing frameworks while acknowledging missing components. Assumptions that work well enough locally to maintain predictive power, but already hint at deeper inconsistencies. And as these nearby systems are cataloged, compared, and averaged, they establish a baseline narrative of how cosmic structures should behave. A narrative that becomes increasingly influential as observations extend outward, because distant phenomena are interpreted through analogies to these familiar cases, even when environmental conditions diverge significantly. And so the nearby universe functions not only as an object of study, but as a reference lens that shapes interpretation itself, subtly biasing conclusions toward continuity rather than rupture. And this reliance on the familiar is reinforced by the practical realities of observation, since closer objects yield higher resolution data, better signal-to-noise ratios, and repeated measurements over time, creating a feedback loop where well-studied regions inform theory, theory guides instrument design, and instruments preferentially succeed where theory already applies, giving rise to a sense of stability that feels earned yet may be partially self-reinforcing. And while this approach has delivered extraordinary insights into the mechanics of stars and galaxies, it also establishes expectations about scale, symmetry, and causality that are rarely questioned until evidence forces a revision, leaving open the possibility that what appears consistent nearby may not generalize cleanly to more extreme environments, a possibility that remains dormant at first, subtle and easily overlooked, until observation pushes just far enough that familiar patterns begin to strain under conditions they were never meant to explain. And as observation moves beyond these nearby reference points and begins to sample environments that differ not just in distance, but in age, density, and energetic history, the quiet assumptions formed from local systems start to weaken, because the farther we look, the less the universe resembles a scaled-up version of what we already know, and the more it begins to behave like a record of changing rules, rather than a single coherent state. Since distant galaxies are not merely far away in space, but displaced in time, observed during epochs when matter was distributed differently, radiation fields were stronger, and structures were still assembling rather than settling into equilibrium, which means that the familiar relationships between mass, light, and motion no longer align as neatly as expected, forcing astronomers to confront a subtle but profound shift in perspective, where the universe is no longer interpreted as a static system extended outward, but as a sequence of transitional phases stacked along the line of sight, each governed by conditions that cannot be reproduced locally. And this is where the first major strain appears, because methods that worked reliably nearby begin to produce ambiguous or conflicting results when applied at scale, as galaxies that appear small and irregular by modern standards exhibit unexpectedly high rates of star formation, extreme luminosities, and chemical signatures that suggest rapid evolution rather than gradual refinement, challenging the assumption that cosmic structures grow slowly and predictably, and instead implying periods of accelerated change that compress processes normally spread over billions of years into much shorter intervals, an idea that sits uneasily with models calibrated on the present-day universe. And the tension deepens when gravitational effects inferred from motion and clustering begin to diverge more dramatically from what visible matter alone can account for, requiring increasingly dominant unseen components to maintain consistency across scales, components that do not emit light, do not interact electromagnetically, and reveal themselves only through their influence on structure formation, subtly shifting the role of observation from direct detection to pattern recognition, where the absence of expected behavior becomes as informative as any signal. And at this point, the act of looking farther outward begins to expose a conceptual limit rather than a technical one. Because while instruments continue to improve, the interpretive framework struggles to accommodate environments that do not resemble the universe we inhabit now, raising the possibility that some of our most trusted intuitions about causality, hierarchy, and progression may be artifacts of temporal proximity rather than universal principles. And this realization introduces an unexpected consequence. Namely, that expanding the observational horizon does not simply fill in missing details, but actively destabilizes the narrative constructed from nearby systems. as evidence accumulates that the early universe was not a quieter, simpler version of the present, but a fundamentally different regime where density, temperature, and interaction rates conspired to produce behaviors that appear extreme or anomalous only when judged by modern standards, suggesting that continuity across cosmic time may be the exception rather than the rule. And once this is acknowledged, the role of scale itself must be reconsidered, because distance no longer functions merely as a measure of remoteness, but as a filter that selects which physical processes remain visible and which fade below detectability, biasing interpretation toward the most energetic, luminous, and resilient phenomena, while quietly excluding subtler structures that may nonetheless dominate the universe by mass or influence. And in doing so, large-scale observation begins to privilege certain narratives over others, not by intention, but by necessity, creating a situation where what we describe as the structure of the universe may be skewed toward what survives observation, rather than what is most representative. And it is here, in this transition from the familiar to the temporally distant, that a first assumption finally cracks. Because the idea that the universe can be understood by extrapolating outward from what is closest and clearest starts to look increasingly fragile, hinting that proximity has shaped our confidence more than we might like to admit, and that the deeper we look, the more we are forced to question whether the universe is revealing its true nature or merely exposing the limits of a perspective built from a single moment in cosmic history. And once that fragility is acknowledged, a more uncomfortable realization begins to surface, because the challenge is no longer confined to interpreting distant data, but extends to questioning whether the conceptual tools we rely on are capable of describing the universe at all scales. Since many of the frameworks that organize modern cosmology are built on an implicit assumption that complexity emerges gradually from simplicity, that early conditions set broad constraints, while finer structures crystallize over time, and that by tracing this progression backward, we can reconstruct a coherent origin story. Yet mounting evidence suggests that this assumption may be inverted, because the earliest observable epochs do not present themselves as orderly foundations, but as turbulent, densely interconnected environments where rapid interactions dominate, and where distinctions between structure, background, and noise blur into a continuous field of influence, implying that what we consider complexity may not be an endpoint of cosmic evolution, but a persistent feature that merely changes expression as the universe expands. And this reversal carries significant consequences, because if early cosmic conditions were already rich in interaction and variation, then the apparent smoothness of the present universe may be less a natural outcome and more a product of dissipation, dilution, and observational bias, meaning that the clarity we associate with proximity and maturity could be masking a deeper continuity of underlying processes that never truly simplify. And this perspective reframes anomalies not as exceptions to a stable rule set, but as reminders that the rule set itself may be context-dependent, valid only within certain density ranges, energy scales, or temporal windows, which becomes increasingly apparent when attempting to reconcile observations that demand invisible components to preserve consistency across scales, as these components are introduced not because they are directly observed, but because without them, the mathematical coherence of the model collapses, revealing a reliance on internal consistency rather than empirical completeness. And while this strategy has proven remarkably effective at producing accurate predictions, it also introduces a subtle circularity, where theoretical constructs gain legitimacy through their necessity rather than their detectability, blurring the line between discovery and accommodation. And it is here that the second major assumption begins to fail, namely, that observation leads theory in a clean, hierarchical fashion. Because in practice, theory often defines what counts as observable, shaping instrument design, data selection, and interpretive thresholds in ways that quietly filter reality before it ever reaches analysis, creating a feedback loop where the universe is interrogated using questions it has already partially answered. And this becomes particularly problematic at extreme scales where signals are sparse and ambiguity dominates, because under such conditions, even small interpretive choices can propagate into large cosmological conclusions, transforming provisional inferences into structural pillars. And as these pillars accumulate, they begin to support a picture of the universe that is internally consistent yet increasingly abstract, populated by entities that influence everything but remain inaccessible to direct confirmation, raising the possibility that our most successful models function less as mirrors of reality and more as compression algorithms that reduce overwhelming complexity into manageable forms, preserving predictive utility at the expense of ontological clarity. And if that is the case, then the tension between what is observed and what is required by theory is not a temporary gap awaiting better instruments, but a structural feature of how knowledge is constructed at cosmic scales, suggesting that some aspects of the universe may be permanently inferred rather than seen, not because they are hidden in principle, but because the act of observing at such scales inevitably collapses rich, multidimensional processes into thin streams of data, forcing understanding to emerge from patterns rather than presence. And this recognition introduces a deeper unease, because it implies that the universe we describe is shaped as much by epistemological constraints as by physical ones, and that the further we push toward extremes of distance and time, the more cosmology begins to resemble a negotiation between coherence and humility, where explanatory power is gained not by revealing a final structure, but by accepting that some assumptions must be treated as provisional scaffolding rather than foundational truths, leaving open the possibility that the most fundamental features of the cosmos are not waiting to be discovered as objects, but to be recognized as limits imposed by the way reality interacts with observation itself. And when those limits are acknowledged rather than resisted, the focus of inquiry shifts again, away from refining existing structures and toward identifying the boundaries beyond which current methods cease to function as intended. Because at the largest scales and earliest times, the universe does not simply become harder to see, it becomes qualitatively different to describe. As signals thin out, correlations weaken, and the assumptions required to translate observation into physical meaning begin to dominate the results themselves, a transition that is most evident near the observational horizons that define modern cosmology, where expansion stretches light to the point that information degrades faster than instruments can compensate, and where entire regions of spacetime recede beyond causal contact, rendering them permanently inaccessible, not because of technological limitation, but because of the geometry of the universe itself. And this introduces a hard frontier that cannot be crossed by better resolution or longer exposure, forcing science to operate with a finite dataset that shrinks relative to the totality it seeks to describe. And within this constraint, even fundamental quantities lose their intuitive grounding, because measures of distance, age, and density become model-dependent, inferred through chains of assumptions that compound uncertainty with each step, so that at the edge of observability, the distinction between measurement and extrapolation becomes increasingly symbolic, representing coherence within a framework rather than direct engagement with reality. And this is compounded by the fact that many of the most influential processes shaping large-scale structure may leave no persistent, localized signatures, instead operating through cumulative effects distributed across vast volumes and timescales, meaning that their presence can only be inferred, statistically, if at all. And as a result, the universe at its largest extent begins to resemble an underdetermined system, where multiple incompatible explanations can fit the same limited evidence, not because one is correct and the other's false, but because the data itself cannot discriminate between them, placing cosmology in a regime where progress is measured less by convergence on a single narrative, and more by the elimination of internal contradictions. And this methodological shift reveals another boundary, one rooted not in physics, but in inference. Because as uncertainty grows, models must balance explanatory reach against falsifiability. And beyond a certain point, increasing abstraction preserves coherence at the cost of empirical anchoring, producing theories that are mathematically elegant, yet observationally elusive. And while such frameworks can offer profound insights into possible structures of reality, they also blur the line between description and speculation, especially when they invoke domains or dimensions that lie entirely outside observational access, raising the question of whether these constructs extend knowledge or merely stabilize existing paradigms under extreme conditions. And this tension is not a failure of science, but an inevitable consequence of confronting a system that vastly exceeds the scale at which verification is possible. Because the universe does not present itself as a closed experiment, but as an open-ended process whose most fundamental features may operate beyond any horizon we can probe. And in this context, the role of cosmology becomes less about assembling a complete inventory of what exists, and more about mapping the contours of what can be known, identifying which questions admit empirical answers and which dissolve into dependence on initial assumptions. And it is here, at this frontier, that the third and most subtle thinking turn emerges. Because the ultimate limit may not be the absence of data or the weakness of instruments, but the structure of inquiry itself, shaped by the necessity to compress an incomprehensibly large and dynamic reality into finite representations, suggesting that some uncertainties are not gaps awaiting closure, but stable features of the relationship between observers and the universe they inhabit. Features that persist no matter how far observation advances. And once this is recognized, the search for a final, all-encompassing explanation begins to look less like an achievable destination and more like an organizing ideal, guiding exploration while remaining perpetually out of reach. Not because the universe withholds its secrets, but because, at a certain scale, explanation and observation diverge, leaving us navigating a landscape defined as much by epistemic boundaries as by cosmic ones. And if that divergence is accepted not as a temporary obstacle, but as a defining feature of our relationship with the cosmos, then the question subtly shifts, once more, away from what the universe ultimately is, and toward what it permits us to know. Because at every stage of inquiry, the picture we assemble is shaped by a convergence of constraints that are rarely acknowledged simultaneously, including the finite speed at which information travels, the selective survival of signals across expanding space, the compression of continuous processes into discrete measurements, and the necessity of translating raw data into conceptual frameworks that prioritize coherence over completeness, all of which conspire to produce a universe that appears structured, hierarchical, and intelligible, even if those qualities emerge as much from the act of description as from the underlying reality itself. And this raises a final, unresolved tension, because if knowledge at cosmic scales is inherently filtered, then the absence of definitive answers may not indicate ignorance in the conventional sense, but fidelity to the limits imposed by observation, suggesting that uncertainty is not a flaw to be eliminated, but a signal that inquiry has reached a regime where questions outpace verification. And in such a regime, the demand for closure begins to distort understanding, encouraging narratives that resolve tension prematurely rather than accommodate ambiguity. Yet the history of cosmology repeatedly shows that its most transformative insights arise not from decisive conclusions, but from moments when established explanations fail quietly, leaving behind gaps that resist immediate interpretation, gaps that persist long enough to reshape the direction of inquiry itself. And it is within these unresolved spaces that the universe exerts its strongest influence on human thought, not by revealing hidden structures outright, but by exposing contours of what cannot be settled within existing paradigms, forcing a reconsideration of how explanation, evidence, and meaning intersect at extreme scales. And this reconsideration carries implications that extend beyond cosmology, because it challenges a deeply rooted expectation that reality must be fully articulable, that with sufficient data and refinement, the universe will eventually resolve into a complete and self-consistent account, when it may instead remain an open system, whose most fundamental characteristics are accessible only through approximation and inference, never collapsing into a final description. And if that is the case, then the pursuit of understanding becomes less about converging on a single truth, and more about maintaining a dynamic balance between exploration and restraint, between expanding conceptual reach and recognizing where conceptual tools begin to shape outcomes more than they reveal them. A balance that requires resisting the impulse to equate explanatory power with ontological certainty, especially when dealing with domains that lie permanently beyond direct engagement. And so, the universe that emerges at the end of this inquiry is neither fully known nor fundamentally unknowable, but suspended between description and silence, offering enough structure to sustain inquiry while withholding enough certainty to prevent closure, leaving us in a position where each advance clarifies not only what can be said, but also what must remain provisional. And perhaps the most accurate account of the cosmos is not one that resolves its mysteries, but one that remains open to revision without demanding completion. Because the moment explanation claims finality, it ceases to reflect a universe that is still unfolding, still receding, and still filtering itself through horizons that no observation can cross, inviting us not to arrive at an answer, but to remain attentive to the space where answers fail to fully form, and where understanding persists precisely because it has not yet reached an end.